Yeah, it's an honor to introduce today's seminar speaker. The first CITA seminar of 2025 is Dr. Steve Vance from JPL. And Steve is, I think, heads the planetary interiors and geo. Is that? No.
So there was a time when I was the manager for the planetary interiors and geophysics group at JPL. Now I'm the deputy manager of all of planetary science, which is about 100 people.
Oh, okay. Great. Yes. And Steve is an astrobiologist and geophysicist. And today he'll tell us about exploring the habitability of the solar system's ocean world using geophysical measurements. And should I drag on this introduction, Dylan?
A little bit.
Okay.
or I can vamp. I can also vamp on the first slide. Why don't I do that?
Okay. Well, I can say other facts that I remember about.
Okay, sure.
So Steve got his undergrad degree in physics at UC Santa Cruz and his PhD from the University of Washington.
In Seattle.
In Seattle, yeah.
Amazing.
That's all.
Yeah, I might have been hard pressed to remember those details. Not about myself, mind you. Yeah, so thanks so much for everyone for coming to the talk. Thanks CITA for hosting me. I'm here today and tomorrow. I'm staying in Massey Hall just down the road. Who knew that? How did that even get connected? That's really interesting. Oh, I see it's connected to the computer. Yeah, so I'm around if folks want to talk to me after this. That's cool. That works. Why don't we put it the other way? Sorry. I hope you see me. Hi. I'll put this down here. I'll turn on my camera.
I can also.
Yep. Thanks everyone here and online for bearing with us. I made a somewhat exceptional request to have this thing blocking my face so that I can sort of jump from slide to slide if I so desire. This is wonderful. Now I just have to do this. Hang on, please bear with me. And that is not what I want to do. I'll just swap displays. Okay, so folks should be seeing this. Great. And here we are. So let me back up a little bit. Okay, so yeah, I work at the Jet Propulsion Laboratory, effectively one of NASA's many field centers. We're the place that builds the rovers. We also have built the large exploration satellites that have explored the outer solar system. That would be the Voyager spacecraft, 2 of them, and then the Galileo, and then Cassini, New Horizons. I guess New Horizons we did not build. Anyway, we built a lot of large spacecraft, so sending robots into the solar system to learn more about planets. And I'm excited about the solar system's ocean worlds, places where there's lots of liquid water under a surface of ice, not least because they might tell us something about watery exoplanets, the kinds of planets that don't exist in our solar system. So Earth-like planets that are far from their star, covered in ice, but possibly have extensive subsurface oceans that might host life. So in this image drawn by famous science illustrator Don Davis, who did the illustrations for the Cosmos in the 80s, we're depicting active seafloor hydrothermalism, both high temperature in the distance and low temperature closer to the foreground, venting material into the ocean that might support life independent from energy from the host star, and interacting with an ice shell that is geophysically interesting and active in a way we think of more akin to how our mantle works, that is undergoing solid state convection, possibly lots of interesting dynamics and chemistry in the ice itself. All of that interacting with a surface with rich geology and possibly spewing materials from the ocean, possibly containing hints of life into space. So this is deliberately depicted as a watery body orbiting a planet that does not exist in our solar system. So the overall message, the outline for the talk, things that I hope you come away with today are that ocean worlds are vast potential habitats waiting to be understood. Europa Clipper, our most recent large robot explorer, it will conduct an integrated investigation to understand the habitability of Europa, Jupiter's ocean moon. And my group and the extended list of authors, some of whom I listed here, are combining laboratory studies with computer modeling to prepare for the analysis of Europa Clipper and other mission data in order to understand the salinity of Europa's ocean and thereby more about its habitability. So to elaborate on this point that I made about these being analogs for oceans in other solar systems, here's a graphic that I like from a paper by Olivier Grosset from 2013. This was at the dawn of the JUICE mission. This is ESA's Jupiter Icy Satellite Explorer, which is also on its way to Jupiter. This is just pointing out that there are many types of stars shown on the y-axis. Ours is the middle type. I imagine there are many of you in the room who know more about this sort of thing than I do. But in our own solar system, Earth resides in the region where liquid water is stable at the surface, the so-called habitable zone. This is the focus for a lot of the efforts to understand exoplanets around other stars. There's a search for Earth 2.0, to try to understand in the next 20 years, using the Next Generation Space Telescope, whether we might be able to find a world like ours with signatures of life. The revelation in the last 20 or 30 years has been that there are many moons of the large planets in our solar system that likely have lots of liquid water under their surfaces. This is a revelation that has been enabled by first Voyager and then Galileo and then Cassini. We're excited to follow up with the next generation of exploration. So thinking about this extended habitable zone, that is the region where liquids can exist under the surface, we can divide that even further and think about how those habitable regions might differ as we move farther from the host star. So this is showing also decreasing distance from the sun or the host star going to the right. And it's showing that there are many different frost lines. So not only water condensing, but also at Jupiter, and with its large satellites shown here in order of distance from Jupiter, you have the condensation also of carbon dioxide and sulfur compounds. And then when you get out to Saturn, with its many small satellites and one that's very large, incidentally, these three largest satellites are all about the size of the planet Mercury. So these are big worlds, planets in their own right, if they were orbiting the sun, and not a large planet. So out at that distance, you have ammonia and methane condensing. And so you could imagine worlds that are very different from ours. This is another reason why these are important places to explore, because they challenge our concept of how planets work. Yeah, and we really don't know that much about the next planets out, Uranus and Neptune. And indeed, a priority of NASA's exploration for the next 20 years is to develop a Uranus orbiter and probe. There are also efforts to develop some kind of mission in our lifetimes to explore Neptune. So as indicated here, one point of interest there is that the moons likely have oxygen condensed at their surface, and out at Neptune, they also have nitrogen. And in fact, Neptune's only large moon, Triton, has been observed to have some kind of venting from its surface, likely in the form of nitrogen that's devolatilizing at the surface, possibly due to some kind of subsurface activity. So there's a lot to understand, a lot to explore, a lot of interest for a lot of different aspects: geophysical, geochemical, geological, and the exploration of possible life is one of the goals there. So we're at a really unique time in that exploration, in that, as I mentioned, there are two missions that are already on their way to Jupiter. And so those are ESA's Jupiter Icy Moons Explorer, or JUICE, and NASA's Europa Clipper. So those launched in the last couple of years. They will arrive at Jupiter in the early 2030s. JUICE will orbit the next moon out from Europa, that is Ganymede, the largest of the icy moons in the solar system. And it will be there at the same time that Europa Clipper is focusing in exploration of Europa. A little farther in the distance, both in time and space, is NASA's Dragonfly mission, which is currently being developed, and I believe they're now in phase C, so beginning to cut metal. that spacecraft will land on Titan's surface. And since Titan has a dense atmosphere, 1.5 times the pressure of our atmosphere at the surface, that is also very cold, and the gravity is low. It's optimal conditions for flying around with a helicopter. So Dragonfly is a quadcopter that will fly around Titan's surface. So that's a very exciting mission design. Hopefully that will reveal a lot of really exciting things about Titan. But this talk I'm focusing on Europa. I'm happy to talk about any of these moons in detail. I've studied all of them using the modeling software that I'll describe toward the end of it. But Europa is representative of the kinds of things, the complex system that we want to study, that we need to study in an integrated fashion to understand the possibility of life. So this is a figure from a paper that I had the honor of leading that was published in 2023 that is summarizing all the different things that Europa Clipper, shown here, will investigate. So you see Europa has this very complex surface with different kinds of linear fractures crisscrossing its surface. These kinds of features are seen over the entirety of Europa. The surface of Europa is less than 100 million years old, as inferred from the lack of craters at its surface. And so you have constant resurfacing of Europa, likely due to flexing of its ice from the tides that are caused by its eccentric orbit around Jupiter. And so all of that activity hints at something happening in the ice. I mentioned the ice should be thought of as a geophysical entity, more similar to our mantle than to sea ice, because it's many kilometers, if not tens of kilometers thick. And so we can ask if there are fluids within the ice that are there for long periods of time, if those fluids are over some period of time flowing downward, perhaps analogous to rivers, and reaching the ice, and if materials generated at Europa's surface by impacts and by the intense radiation environment that Europa is bathed in, because Jupiter's magnetic field grabs onto solar wind particles, if that process leads to changing chemistry in Europa's ocean. So we want to know not just what is Europa's ocean chemistry, but how is it being influenced by the space environment. So we want to understand how thick the ice is, what are the properties of the ocean, and zooming out on the left here, what are the properties of the deeper interior, and might there be the kind of volcanoes that I indicated in that first figure. So this is the paper. I encourage you to check it out if you're interested. I can share it with you if you email me. My email is on the first slide, but feel free to bug me for my email. Lots of people are involved in Europa Clipper. This is just a subset of people on the science team. Technically, the habitability investigation of Europa involves the entire team. These are the people who contributed directly to the writing of this paper. But just emphasizing it's a very large science team, about 200 people, plus a lot of graduate students, postdocs and such, so people coming on and off of the project. So getting into kind of the NASA speak, describing how we present Europa Clipper and what the agreement between JPL and APL, the Applied Physics Lab in Maryland, those are the institutes developing the mission and running the mission. They've developed and are operating the mission as an agreement with NASA. There's a certain return that's expected from NASA. So we have level 1 requirements about understanding Europa that I'll describe in some detail. And so you'll have to excuse me if I use a certain kind of vernacular, and I encourage you to ask questions if you have any. But the first parts of this are actually pretty easy to understand. So these are the Galilean satellites of Jupiter. They're called the Galilean satellites because Galilei discovered them 415 years ago. I just saw an article in my newsfeed today noting that. And so this is what we knew of them 415 years ago, these scribbles just above the imagery, right? And he watched these on successive nights change their positions. And from that, in part, inferred that these are objects orbiting Jupiter, and that Jupiter is itself a planet. So the understanding of Jupiter is intrinsic to our dawning understanding over the last 400 years about our place in the solar system, and then in the galaxy, and then in the universe as a whole. So these are the large moons of Jupiter as we see them today. This is thanks to the Galileo spacecraft that finished its tour of the Jupiter system in 2003, flying into Jupiter. But on its tour of these moons, it revealed that Io is the most active volcanic body in the solar system, more volcanically active than Earth, spewing material into space. And all of that is by virtue of the intense tidal flexing that happens in Io's interior. And there's currently a discussion about whether Io has an interior magma ocean, or whether the magma is more localized. In any case, we know there are lakes of lava sitting at that Io's surface currently. So it's really interesting to think of. And to think of that in connection to Europa, the next body out, which probably receives about 10% of the heat input that Io receives. If all of that were to go into the seafloor, you would definitely have volcanism at the seafloor. Or at least you would have melting of rock, and it's possible that the overburden pressure of the ocean would not be such that the lava could not escape. That's a current topic of discussion as well. And there are questions about how the overall system evolved, the exchange of material between the different moons. You can see that the surfaces are very different. I mentioned Europa is crisscrossed with fractures. You can also see there's this reddish discoloration across the entire surface, which owes to probably radiolytic alteration of some kind. Either defects in salt crystals that are at the surface, has been demonstrated by some lab experiments, or the creation of materials that are reddish just by their nature. In any case, there's a lot of non-icy material on the surface of Europa that is, some of which is probably coming from underneath, probably from a salty ocean. Ganymede also shows some signs of activity. You can, just looking at it, you can see some pock marks, which are indicative of craters. So it's an older surface, still somewhat young. It looks like there are ridges, coherent pieces of material that have moved together. And so there's likely some kind of activity happening in the ice as well over some time scale. Callisto, by contrast, is very old. It's one of the most heavily cratered bodies in the solar system. And so these have all experienced very different histories. JUICE will try to explore the whole system to understand how these satellites work together. The stated goal of Europa Clipper is to study Europa only, but we can talk about whether that's specifically the case. Okay, selling point for this mission, Europa. Yep, please.
Just how much of the Io's water has been lost by sublimation?
Yeah, so right, one can ask, was Io once an ocean world like Europa? And that's part of the discussion about the evolution of these bodies. It seems reasonable to suppose that all of the moons formed by accretion, analogous to what probably happened in the solar system as a whole. There was a subnebula at Jupiter. So as Jupiter condensed, you had solid materials accreting at some distance to form what became the moons. And yeah, Io probably had a lot of water. And one supposition is that much of that water eventually desorbed and migrated outward. I don't think that explains entirely why the outer moons are as large as they are. It's not really well understood. So the short answer to your question is I don't know.
But the slice you showed through Europa showed to be differentiated with, I guess, rocky material at the center. And
yeah,
well established.
Yeah. So let me elaborate on that a little bit. One foible of the way I put together this talk is that I don't get into a lot of the geophysical evidence that we have, which is, after all, the main focus of my interest here. So let me just say on the density concentration question, that whether Europa is differentiated, all of our information about this comes from Galileo, which did a number of fairly close flybys within 1,000 kilometers of Europa's surface and was continuously communicating with the Earth by radio. And so the Doppler shift of that radio signal allowed for the piecing together of the influence of Europa's gravity. And so by mapping that spatially, you can get a sense of the density structure. You get the coefficients for the spherical harmonic expansion of Europa's gravity potential. And so the second order coefficients give you the moment of inertia of Europa. And that moment of inertia is consistent with a water layer that's between 80 and 170 kilometers thick. That range depending on your assumptions about the density of the interior, how dense the rock is, and whether there's an iron core. So there have been a few papers recently interpreting in the statistical sense, whether Europa has a core or not. There's a paper led by a colleague, postdoc working with us, that's coming out in Nature Astronomy at the end of the month, that asserts that it's less likely that Europa has a core, which is interesting because it says something about the highest temperature that Europa would have achieved. And there was an earlier paper by a graduate student at University of Arizona asserting that because Europa probably formed cold that is a lot of the nebula that I mentioned earlier had already dissipated, then Europa probably did not have sufficient heat to both melt and devolatilize water from the interior to create the ocean, and also reach a high enough temperature to melt iron at a higher melting temperature that would then migrate down to form a core. So instead, most of the heat of formation of Europa, heat of differentiation of Europa, went into forming the hydrosphere. Yeah. It's a very, very long answer, but thanks for letting me talk about some other work that's been done. The other thing that I'd like to mention that lets me show you a really cool animation by my colleague Corey Cochran is that Europa is embedded in Jupiter's magnetic field. So this is showing the field lines of Jupiter's immense magnetic field, something like 30,000 times stronger than Earth's magnetic field, which captures solar wind particles, as I mentioned, embeds Europa in this intense radiation environment. But because the field is tilted, and because Jupiter rotates at a period of about 11 hours as seen from Europa, Europa sees a changing directional field. The three vectorial components of the field are changing, and in fact, some of them are changing sign over that 11-hour period. And so the main evidence we have for a present-day ocean under the surface of Europa is the induced magnetic field signature depicted here. So this is showing the response of Europa to Jupiter's changing field. So a mini magnetosphere that is entirely due to the induced response that has been attributed to a strong electrical conductor near the surface, which can best be explained by salts in an ocean. So we'll get into that a little later, but suffice to say, that has been an important line of investigation, and one that I'm excited about trying to add some more nuance to our laboratory measurements and computer simulations. So, okay, back to the big picture cell for the mission. So we want to know if Europa has the ingredients for life. This happens also to be the slogan of a grocery store chain in California, which I find amusing. But different story there. So for Europa, ingredients for life means, does it have lots of water? We think it does. We want to confirm that. Does it have the essential elements that life uses? So biologists will tell you that the main elements that we need are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and some other stuff, right? We use magnesium, manganese, all these different things in small amounts, but the schnapps those are the main things that we use, right? So we want to know the distribution of those in Europa, how they're concentrated in different areas, and whether they might come together in proportions that are consistent with supporting life. And are those things organized in a way where they're constantly in chemical disequilibrium? That is, are there opportunities for life to metabolize and hasten the equilibration? Or is Europa just at chemical equilibrium and there's no more interesting geochemistry happening, let alone chemistry amenable to life? These are questions we hope to address. And of interest at Europa, we think that the energetic inputs to Europa that I just told you about have persisted over the entire history of Europa. So as on Earth, we have the prospect of an energetic environment in which life might be able to not only take hold, but evolve over time. So we can think about understanding how life might have evolved, or even if it were abundant enough, influenced the chemical direction of Europa, as has happened with the rise of oxygen on Earth, which is coupled to plate tectonics and subduction. Is there a kind of a Gaian effect at Europa, as some have described the role of life on Earth? Okay, so the mission science, the way we've organized the mission, in order to get at all these different questions, is understanding the ice shell and the ocean. So both confirming the ocean, but also understanding how thick the ice shell is and how the ice shell works. This is mainly a geophysical investigation, but also understanding the composition of the ocean, largely by understanding the surface, both materials excavated from the surface by impacts and by radiation, but also using spectroscopic imaging of the surface. So near-infrared spectroscopy mainly, but also UV and thermal to some extent. And then using visual imaging mainly to study the geology. And so here you can see some beautiful imagery from Galileo of, here especially, different fractures at different scales that have built up these ridges. These ridges are about 20 kilometers across. We think they formed by successive opening and closing of a fracture that exhumes material and builds it up on the fringes. That hypothesis should be confirmed. But if that's what's happening, you can see that happens at a lot of different scales. And by mapping the surface at high resolution, we can begin to do the very complex stratigraphy that's needed to unpack the history of the surface. That is going to involve probably a lot of AI, or what I used to say, a lot of grad students, but we'll see. Maybe there's a role for both. Along with that, we will be looking for signs of activity on Europa, both in the form of plumes, so that's what's depicted here. In 2014, a paper was published in Science by our colleague and Europa Clipper team member, Lorenz Roth, using the Hubble Space Telescope, the UV imaging of the Hubble Space Telescope. And they saw abundances of hydrogen and oxygen commensurate with water that persisted around the south pole of Europa for a period of about 7 hours and seemed to rotate with Europa. So that was deemed to be consistent with an active emission from Europa. Now, that observation has not been repeated. There have been a couple of, maybe 5 high-profile papers, both trying to reproduce such an observation, but also hypothesizing that something like that might have happened during the time of the Galileo flybys. It's still unresolved. This generated a lot of excitement, rightly, not least because it bears an analogy with Saturn's moon Enceladus, where there's a continuous plume that has been linked to a subsurface ocean, and it's in some sense used to constrain the composition of the ocean at Enceladus. Now at Europa, I think it's been established that plumes, if they exist, are not persistent. I'm skeptical if the mechanism would be the same on Europa as it would be at Enceladus. There are other kinds of activity we can look for also. Just, are the blocks moving? Is there less dramatic stuff happening on the surface? But that would still be of interest. And lastly, there is a goal to do reconnaissance. So this is Europa at the highest resolution. There are only a few images like this that Galileo took. But here you can see one of those ridges at high resolution, and you can see lag deposits, the dark material, which is likely, I think at this point, it's likely carbon-rich material, but also salts that has fallen gravitationally down to the bottom, the lowest point. And so you can ask, what are the composition of the material, how did it develop? But also you can see that the ridge and the one next to it have been entirely disrupted by some chaotic features. There are many of these chaos terrains on Europa, places where the entire surface seems to have been disrupted by some catastrophic event. One really compelling hypothesis proposed by my colleague Brittany Schmidt is that these are places where underneath you have a diapir of warm ice rising in a solid state convection kind of mode. And then you have brine or salt-rich ice that melts at the eutectic temperature, so at a very low temperature. But once the melting happens, you have a volume change, and the whole region sinks. And so that gives you your destabilization. And that could actually be a runaway process where once you lower the region, then salts from around there start to fall into it as well. So all of this needs to be verified, but it's kind of a really interesting, compelling idea. And one could even ask, okay, if you develop a lake a few hundred meters thick that's near eutectic, is that at all an environment where life might exist even near the surface of Europa? So interesting things to think about. Lots of rich science, as I mentioned. So all of this will be explored in the spacecraft. It's solar powered. And so this is the Europa Clipper as it was launched. That is, there have been a lot of changes to the design of the mission. We've added and taken away solar panels. It was realized early on in the mission design that the ice penetrating radar, one of the most exciting investigations on the mission, that is, we're going to see through the ice using radio waves, that the antennas for that had to be integrated with the solar panels because the solar panels themselves act as part of the antenna. So there was a whole lot of engineering development that had to be done to design a radar antenna that was integrated with the solar panel. And that also imposed pretty heavy requirements on the spacecraft in terms of electromagnetic interference. It's a very electromagnetically clean spacecraft. You see this magnetometer boom sticking out. We have a magnetometer investigation to explore Europa. And thrusters to position Europa. We'll fire those only when we're far away from Europa. We don't want to contaminate our measurements. The other thing to point out here is that, and this gets really at the mission design, is that all of the imaging instruments are downward pointed. They're all pointing in the same direction, and they're all bore-sighted, so they will see exactly the same region of Europa, at least within their fields of view, and they can operate at the same time. We have enough power to do that. That sounds like a trivial consideration, but it was not the case on the Cassini mission. They were pointed in all kinds of different directions, and it meant that for a given flyby of a moon, the instrument leads for the different instruments had to make a case for why their measurement was the most important. We don't have that problem. And so then you see the forward-pointed instruments. Those are two mass spectrometers, a dust and a gas mass spectrometer, that together will sense materials in the atmosphere of Europa. And so that'll be another part of our in situ investigation. So the trajectory of the spacecraft, we're in its current mode, getting to Jupiter. We launched last October. I was happy to be there and see the launch. That was a very emotional moment. Not least because a giant hurricane came through and the eye of the hurricane was on Kennedy Space Center at the minute that we were supposed to launch. Suffice to say, we delayed for a few days. Yeah, a lot of people were there when the hurricane happened. I decided to come later. But we're on our way, and in February of this year, we will have a close flyby of Mars. So stay tuned for that. We should get some imagery, get to test out the instruments. And then weirdly, we'll come back to Earth. So we're using Earth and Mars for gravity assists to get to Jupiter. And then we get to Jupiter in April of 2030 and begin a process for about a year of getting into orbit around Jupiter. So you might ask, why are we, or maybe I haven't emphasized this, we are not orbiting Europa, as you might think that one would naturally do after Galileo already flew by Europa a bunch of times. We're not going to do that because we want to avoid the intense radiation environment that Europa is bathed in. So I'm going to show you an earlier trajectory, but an image of the entire duration of the mission after the arrival shown here, and showing the buildup of radiation. So there's Jupiter, there's Europa Clipper on its first pass of Jupiter, building its elliptical orbit, making it smaller and smaller through encounters with the different moons. So firing its thrusters at select times to dramatically lower its orbit, so getting closer to Jupiter. And you can see on the upper right, you can see the radiation dose, the accumulated dose in rads going up. We cannot exceed 3 megarads during the lifetime of the mission. So we're about halfway through at this point. But you can see that the other moons, Io in particular, going around really rapidly, because you can see on the upper right, time is going by very fast. So of note here, we're in a resonance with Europa's orbit, and so we're processing and encountering Europa at different times in its orbit, which is really important if you want to sample the tidal response of Europa and also Europa's response to Jupiter's magnetic field. We want to find the peak in the induced response of Europa and also in the tidal response of Europa. So, as I mentioned, multiple flybys. Here's another nice image. So multiple gravity assists to change the position where we encounter Europa. So each of those flybys is not only a different part of Europa's orbit, but also a different part of Europa itself. The entire first half of the mission is just the anti-Jovian part, the part of Europa that is facing away from Jupiter. And the second half is the sub-Jovian part, which is a little riskier, it's higher radiation. Yeah, the mission we plan on 49 flybys of Europa to build up a global map of Europa. And those red marks that you see there are distances as close as 25 kilometers from the surface. So we'll get very close to Europa, which will allow us to sample in detail its gravity, its magnetic field, and hopefully materials that are wafting from its surface. Okay, so what can I say here?
What's the first thing that you expect to be degraded when the radiation dose exceeds the...
Yeah, so the question is about the effects of the radiation and what we're most worried about. So overall, the strategy is to shield the most sensitive electronics. And so for that purpose, there's a vault that's about this big that has, I think, like a half-inch or an inch of aluminum. And so the most sensitive electronics are shielded in that way. The other thing you can worry about is the optics, so those will cloud up. At least with the electronics, it's expected you can have some annealing if you have defects in a semiconductor, especially the MOSFETs that we bought. Were sold to us with the expectation that they should be resistant to defects in this way. That is, if there's an upset, it will heal over time. It turned out, we learned, and as was described in some detail in the New York Times around last June, those MOSFETs were not operating as they should have. And so there was a strong effort over the summer to understand that problem and to address it. But what was added to the spacecraft is a set of MOSFETs that's not shielded to understand the magnitude of that problem. And there were select transistors that were shielded or to which thermal additional heaters were added to be able to try to accelerate the annealing. But that's the biggest concern at this point. Yeah, it's that the lock of a transistor could cause any of the many switches or amplifiers to not work. Yeah, we'll see what happens. I have lots of stuff about the rationale for the habitability. A lot of this talk walks through the paper that I described to you, but rather than going through those things, I think I want to focus on the mission a little more and get to the laboratory and modeling stuff that I mentioned. But just to say a little more about the instruments, you might want to know exactly what the instruments are and how they work together. So we have a whole lot of remote sensing instruments, all pointed in the same direction. So they go from the ultraviolet, the Europa UVS, through the radio with the reason, the antenna. And in between, we have the imaging suite. So that's a telescope. We have the infrared spectrometer, MISE. We have the thermal instrument, e-Themis. These all have heritage from previous planetary instruments. JUICE actually has an analog to the Europa UVS. It's the same team in San Antonio, Texas that proposed that and built it. Reason has a counterpart on JUICE as well, which amusingly is called RIME. So we'll have both RIME and Reason at Jupiter. And yeah, e-Themis and ICE are heritage instruments from, and MISE as well. Those all have heritage from instruments that have flown to Mars or the Moon. So in the in situ category, which is how we group these things, we have those two mass spectrometers that I mentioned. The mass specs instrument is a neutral gas mass spectrometer with a mass resolution of 10,000. That is, it can see for masses that are lower than 100 AMU to very small fractions of an AMU. So they can see small isotopic shifts, that sort of thing, and distinguish between, for example, carbon monoxide and nitrogen. I think those are the two that overlap. There's some things that are alias each other, but you can actually see from differences in binding energies what the masses are. And so we can get isotopic ratios. We can do all kinds of interesting things that have not been possible for. That is isotopic ratios of things like carbon and oxygen and nitrogen that are difficult to get. Similarly, the CITA, the dust analyzer built by a group in Boulder, Colorado, will be able to analyze dust, so grains of material that are lofted from Europa's surface. These two kinds of measurements were instrumental, so to speak, in understanding the plumes of Enceladus and were used to infer the pH and the composition of the ocean. So the other coupled suite of instruments are the magnetometer, for which I showed you the boom earlier, which will allow us to understand, it will always be on. So it will allow us to understand Jupiter's magnetic field in general, but also the influence of Europa, or the response of Europa, I should say, to Jupiter's magnetic field. So in order to understand that magnetic field, we need to understand the plasma environment, which is a dynamic environment that generates its own transient magnetic fields. So we have a plasma instrument, which is amusingly Faraday cups, just a sensor that there's a cup shape that is called PIMS. So I think that's a kind of a fun little name that arose there. The last thing that we do in the instrument realm is not exactly an instrument, and that is using the radio transmission between Europa Clipper and Earth to measure the gravity field, which I alluded to earlier. So these all work together in a very deliberate way. So we can try to group them and sort of how they get at the different investigations for Europa that I described. So we have the composition, right? These are all the different compositional instruments. We have both in situ and remote sensing instruments that look at that. We have the geology. So there are instruments that do geology for us that also do composition. And some of those instruments that do geology for us are also intrinsic to understanding the interior of Europa. So the mission is designed so everything works together. No one instrument answers any one of the questions that we've articulated. And so, yeah, that's inherent in, again, the reason that things are all pointed in the same direction. So that we can have all of these data to learn things like infrared spectra, molecular masses, UV spectra, these different data sets that go with those types of measurements. So these things then lead to are analyzed, and we have models to understand what they actually mean. So that's how we infer abundances of different materials, exogenous versus endogenous materials, and get at things like ice thickness, density structure of the interior, et cetera, which are of interest. I'm intrinsically interested in those things, but really those are things from which we want to infer habitability constraints. So what's the salinity of the ocean? What kind of organics are present? How is temperature distributed throughout the interior? So we put all of that together, and we hope to get at habitability. So let me take you through a day in the life of Europa Clipper. This is again an earlier view of Europa. We thought we'd be there by 2028. So this is showing Europa Clipper. You can see Jupiter in the distance on the left and Europa coming up on the right. And you can see the magnetometer and plasma instrument are already on. The instruments are listed down there. The names have changed a little bit, but suffice to say, again, plasma and magnetometer are always on. So even far away from Europa, we're doing some global observations, global imaging, stellar occultations, that is looking at using the stars behind Europa to get some compositional measurements. So here we're doing a global thermal map of Europa, and then we'll sweep across Europa with the UV instrument and the thermal instrument. And then we'll do some more imaging. We're still 30,000 kilometers from Europa's surface. As we get down below 10,000 and then 1,000 kilometers, you'll see all the instruments turn on. But we've planned out every single measurement for every single second of the planned trajectory. This is the kind of thing we've done for each of the 49 flybys. Thankfully, it's a fairly repetitive operation. So I'll just let this happen. This is now closest approach. So you can imagine building up a swath of imaging across the surface. And only by putting together all of the swaths that you build up over the 49 flybys, do you get the global map at the resolution that we want. That is better than 100 meters per pixel in places, and better than half a meter per pixel in some places for the reconnaissance. Okay, so yeah.
Will there be coordinated measurements using both Juno and Europa Clipper, or JUICE and Europa Clipper?
I'm glad you asked. So Juno will have finished by that time. So Juno is another spacecraft that I should have mentioned that was designed to study Jupiter, and so it's improved our understanding of Jupiter's gravity, magnetic field, what's happening in the interior, so JUICE and Europa Clipper have stood up a working group consisting of members of both teams, and they will release a report about opportunities for joint measurements. And at that point, I expect that we will ask our respective space agencies.
For going around Europa.
Is there a question?
Okay. You better on our hand in this.
That was before.
Okay.
Okay.
We just have an open mic.
These might come on. So
the short answer is yes. Hopefully there will be coordinated measurements. Happily, these missions can operate independently. But yeah, it's worth noting that they have in some senses, very similar instrumentation. In other cases, they're very different. For example, JUICE has a microwave radiometer instrument that would be very complementary. And yeah, being able to have a better time base on the measurements would also be an advantage of coordinated measurements. So we'll see. Stay tuned. So I have a lot more on habitability of Europa, but let me focus on the salinity and habitability, which is my focus for research, and get into some of the modeling and lab work that we do. So this is funded by NASA's Precursor Science Investigations for Europa program. So happily, we've got 2 or 3 more years to work on this, in addition to some more funding that we recently got to do more lab work. So we can ask, how well do we need to know the salinity, and how well do we think we will know the salinity? So people have, in the last 20 years, been applying geochemical modeling to understand what the composition of Europa's ocean might be. So these are some fairly busy figures if you're not used to looking at geochemical stuff. I'll try to walk you through them. Both of them have axes of log axes of moles per kilogram. Let's focus on the left figure. So this is from a little while ago, asking how might the assemblage of different ions in solution in Europa's ocean differ, either from the early stage of Europa, what we might suppose was more reducing, that is more hydrogen rich. That's shown on the x-axis here, the changing concentration of hydrogen in the ocean, which corresponds to the pH, shown on the y-axis of the lower curve. So we think Europa might have been higher pH early on, as hydrogen was evolved from the interior. through water-rock interactions, high-temperature water-rock interactions possibly. But over time, because of the intense radiation environment of Europa, which breaks apart water at the surface with hydrogen escaping preferentially, you might imagine the ice shell becomes oxygen-rich. And if there's an efficient transport of that material into the ocean, one could suppose that the ocean would become more acidic and lower pH over time. In that case, oxidized materials like sulfate could be more soluble. And in this chemical model of just varying the pH, based on an initial Europa that comprised chondritic materials, just meteorites for which we know the composition, that are likely candidates for the materials that were present at Jupiter when Europa formed. If you just take the fluids that were in those meteorites, form an ocean, interact the ocean with the available rock, you get these compositions. If you make the ocean lower pH, you allow sulfate and magnesium to become more dissolved. So one might suppose that the end members for an oxidizing versus a reducing Europa ocean would be one dominated by magnesium sulfate or one dominated by sodium chloride. That's kind of the take home from that. My colleague, former postdoc Mohit Nalwani Daswani, did a similar set of analyses using a different set of geochemical models, different inputs, and came to the conclusion that Europa might be very carbon rich, and that if you take into account the pressure dependence of solubility of these materials, that you might actually have sodium and chlorine at the top of the ocean, but magnesium more abundant at the bottom of the ocean. So it could be very complicated, and we can ask, is this the sort of thing we can resolve? What if, because of this kind of dynamic, the surface is represented by sodium and chlorine, but in fact, other materials are present at the bottom? Is there a way that we could figure that out? So of interest, something I started exploring just before the pandemic and then spent much of 2020 just sitting in front of my computer in my room thinking about this. You can imagine putting together radial structure models of Europa based on those gravitational constraints that I mentioned earlier. So say you know the moment of inertia, and you suppose the ice is a given thickness, and you suppose the ocean has a certain salinity, and you just happen to have an equation of state for the fluid that gives you the density, sound speed, anything you might want, all in a self-consistent way. Then you can propagate the adiabat, that is the changing density versus pressure, under the assumption that the ocean is convecting. That's a pretty reasonable assumption. It's similar to what we do for our atmosphere. We know our atmosphere is convecting with some caveats. So what you arrive at is that for just two representative ice thicknesses, supposing Europa is either 5 or 30 kilometers ice thickness, you get different temperature structures of the ocean, just depending on what kind of salts you have in the ocean. This is the sweet. So thinner lines are 10% of the salinity of the thicker lines, and dashed lines are magnesium sulfate, and solid lines are seawater. I have an equation of state for seawater. I don't have an equation of state for sodium chloride solutions yet. I will. And so we can ask, how does that map then to the electrical conductivity of the ocean, which is what determines the magnetic induction response of Europa. So we started doing that around, I published a paper about that in 2018. This paper was about then using that information to predict what the magnetic induction signature would be. So the question being, are any of these resolvable or distinguishable from each other? Never mind that there's a whole continuum of different compositions. It's a huge perimeter space. We want to explore it. Let's just see about this more simplified mode. So first we have to ask, what is magnetic sounding? Well, I mentioned to you the induced field. This is just sort of trying to break it down in real simple terms. So we want to determine physical properties at depth using magnetic measurements. So we have to use forward models informed by lab data, and then compare those lab data with spacecraft measurement and choose the best fit. Okay, so the induction response, we have an external field that's applied. As that field changes, it induces a response in the interior that goes in the opposite direction, but should have the same periodicity as the external response. So again, we can imagine flying by Europa and trying to sense that response. It's important to fly by Europa at multiple points in its orbit relative to Jupiter's response, so we can see the changing response. So going into some math of this, what the induction is doing is we're trying to figure out the diffusion of the magnetic field into the interior, which is conditioned by the conductivity sigma shown there. We want to know what salts are dissolved in the ocean, and then over what range of depths are those found. That is, how thick is the ocean? How thick is the ice? So just one mathy slide. Again, diffusion equation, Helmholtz equation, which we solve radially. It turns out the solutions to this problem were worked out in the 60s. There was both an analytical and numerical solution that were described. We went through and digested those and summarized them in the supplement of this paper in some detail. It's a complex response. So you have some oscillation that you have embedded in this K. You're solving this differential equation, and the complex response is of this form. And so the n equals 2, n equals 1 form is the dipole response. It's important to note that if we think that the object we're investigating has a intense ionosphere, there's a lot of bound charged particles above the surface, we can account for that too, assuming that the ionosphere responds on the period of these oscillations, that the ionosphere responds in a coherent way and isn't changing itself in time, which we can discuss. So the complex response has both an amplitude and a phase delay. So if it were a perfect conductor and responded perfectly, it would be in phase. It would have an entirely real component. So if you arrived at Jupiter or at Europa at the peak of the oscillation of Jupiter's field, you would expect to see an opposed field with the given amplitude that would be exactly in time with Jupiter's field. If it's an imperfect conductor, then you have a delay in that field. So this is again why it's important to encounter Europa at different parts of its orbit to sample the shape of that sine curve, the oscillating curve. So we have both a MATLAB and a Python solver for this that we developed. We spent some time thinking about how this works in general as a function of period. We did this for Europa, Ganymede, and Callisto. So on the left, I'm showing that amplitude that I just mentioned. On the right, I'm showing the phase delay. And so these are all the models that I showed you before. Again, thick lines are high salinity, thin lines are low salinity. And the vertical red lines are the different excitation periods from Jupiter's field as seen from these moons. So synodic refers to the rotation of Jupiter. So that's the main one that I described to you. But it turns out we can also look at the orbital period. That is, Europa has an eccentric orbit, which means it'll also see a changing field just by virtue of being at its apex close to Jupiter, and then at the other side of that oscillation far from Jupiter. And so those are both signals that Europa Clipper is designed to see. And just by using both of those signals, we expect to learn a lot more about the interior. For example, decoupling the thickness of the ice from the thickness of the ocean, also decoupling the conductivity of the ocean from its thickness. So we can see that it happens that for the models that I've chosen, the orbital signal is really important for being able to separate very distinct phases in terms of the dependency of the amount of salt in solution. And similarly for the phase shift. And we can ask similar questions for Ganymede and its ocean. And I have this kind of toy question for myself that I'm keenly interested in, and that is whether there might be a salty ocean under the high pressure ice of Ganymede. That's a whole other talk, though I'm happy to talk about that now or while I'm here. It's a really interesting story about the chemistry of high pressure ices, these dense spaces of ice that actually sink in pure water. But if you add enough salt, you can develop fluids that are more dense than the high pressure ice. So
this is for given thickness of the ocean?
This is for a given thickness of the ice, yeah.
Ocean?
So the way we conduct these models, we have a fixed moment of inertia, and we assume a fixed ice thickness. So the ocean thickness actually varies a little bit because we're allowing the seafloor depth to change. It only varies by a few kilometers. Yeah. So it's a slightly different different ocean thickness, and yeah, in other applications that I'll describe a little later, we did fix the ice and ocean thickness, and that broke self-consistency with the chemistry. But it's in a sense a purer way to explore the problem. But for this paper, this is what we did. So it can be pointed out. Firstly, these are just n numbers, right? We really want to approach this more complex problem. Now, a good geophysicist would say that is making it too complicated. You want to make it only as complicated as it needs to be. But for the habitability question, it kind of does need to be complicated. And my colleague, Julie Castillo, it turns out, was working on a related problem at the same time we were working on our paper. pointing out that these volatile components that I mentioned before can have an outsized contribution to conductivity. If you add CO2 to the ocean, you can actually raise the conductivity quite a lot. The conductivities we were considering in the models that I showed you are in the range of 1 to 2 Siemens per meter. So you can see that here. We're less than a Siemens per meter, maybe up to 4. Whereas, that's interesting. Sorry. You can't see that, can you? Good. In contrast, if you add carbon dioxide in this example, or ammonia, you can add. This is the addition to the conductivity in addition to the numbers that I showed you before. So you could imagine conductivity is approaching 10 Siemens per meter, which would give you a different induction response. So it's important to investigate these more complex oceans. And so our project tries to put all this together. This is a 3-part Venn diagram involving experiments, models, and data science methods. And so one major task is understanding ocean electrical conductivity as a function of pressure, temperature, and composition. But that feeds into ice and ocean equation of state, some of which we already have, some of which we're developing based on sound speed measurements and phase equilibrium measurements most of which we have made, but some of which we are going to make. And we feed into that assumptions about the mantle and the core mineralogy. So we can consider that space as well. It's a very complicated, large space, but we hope to try to explore a lot of it. So all of that culminates then in interior structure models, some of which I've kind of alluded to already. We then feed that into a modern data science method, so linear least squares, which we've developed for the magnetic field analysis, but also gravity and radio science, plus magnetic field measurements using Markov chain Monte Carlo. So these are kind of buzzwords in our field. I imagine you also see like Bayesian analysis kind of showing up more in the literature these days. It's kind of where computational stuff is at. And it's fun that this is a more nuanced way to explore things rather than looking at N numbers as we've been doing. And I'm excited how that couples into NASA's movement toward open science. This is the logo for the transformation to open science that NASA has begun. They're requiring any new funded science research to have a plan for open science, both in terms of publications and in terms of making software available. So the radial models that I described are available in this planet profile code that I maintain, and it depends on the CFreeze code that my colleague Baptiste Journeau has developed, which couples in these equations of state for different materials, including ices. So he has the most up-to-date equation of state for water and different phases of ice. And so if you download Planet Profile, you just clone the repository, you can immediately generate all of these figures. It outputs these nice wedges for which there's all kinds of geophysical data that it also predicts. So here's a Ganymede with multiple phases of high pressure ice for a pure water ocean. Here's Callisto with 100 grams per kilogram of magnesium sulfate, showing no high pressure ice, which might be surprising to some people because Callisto is quite large, but also not very well differentiated. Titan, as we touched on before, possible presence of high pressure ice. These are all different things we can do. Io, Europa, Triton, all the way down to the very small moons, Miranda, moon of Uranus. Enceladus is in here too. So all kinds of different stuff that we can do. I'm excited that I have had an undergraduate student this year who incorporated this Reactoro code, which allows us to develop new models. These are outputs of Planet Profile as well. Here showing density versus pressure. These are those temperature profiles that I showed you before. And these different curves are for the different published models of Europa's composition. So this is now getting at that complicated composition. So we're trying to approach it from both directions. That is, trying to get really good laboratory data, but also just using the available geochemistry to do the kind of stuff we want to do. So, okay, let me just jump to a couple more slides with the last part of that. That is the big data part. So my colleague, Corey Cochran, has developed a linear least squares method for looking at magnetic field data over the entire trajectory of emission, taking all the incremental measurements of magnetic field. And I realize I'm over time. Sorry, people need to go. And trying to figure out the most likely solution to a model. So this was for a study we did of Neptune's moon Triton. So I fed him tens of thousands of models of Triton, both with and without an ionosphere. So the likely cases for an ocean are shown in blue. There's some less likely cases for geochemical, geophysical reasons. The gray are less likely, but we did model them. And the line, the magenta line here, is the case with an ionosphere only. So the other models also included the ionosphere. Just we wanted to contrast those with the null hypothesis of just an ionosphere. And so from the measurements that he analyzed, these are simulated measurements for this candidate mission we were proposing. This was the outcome. This is supposing that there is an ocean. This is still forward modeling. I just want to emphasize that. But he's published a couple papers describing this method, and we're excited to apply it in the context of Europa Clipper. Our other colleague, Flavio Patricia, he just got his PhD, he's postdoc with us, published this nice paper recently showing simulated gravity constraints based on the Galileo mission. So using Galileo gravity data, but assuming a seawater ocean, just pointing out that the problem is alias. That is, if you know the ocean thickness to a certain amount, you also know the ice shelf thickness. They're coupled, but the current constraints only allow you to say that is the coupling. Right? There's a linear relation between them. Okay, if you, for this assumed seawater ocean, if you then take into account the magnetic induction for which he included in his coupled model, then you get this answer. It looks more like a Gaussian in both of those quantities, right? So that's kind of nice. So this is the kind of thing we can imagine doing, but you can imagine adding many, many dimensions to this. And I'm sure if you've looked at these Monte Carlo analyses, you're familiar with corner plots that kind of try to put all that together. So I want to apologize for running a little bit over time. I guess we had a little bit of delay at the beginning. And I'll just, I have more things that I could show you. There's lots we can talk about, but I hope I've given you a flavor for the kind of work we're doing and why Europa Clipper is exciting. So happy to take any questions. I saw one in the chat, which was just, are we considering an Enceladus mission? NASA tries to follow the recommendations of the National Academy of Sciences, which put out its decadal survey of planetary science, which recommended a Enceladus flagship mission as a second priority to a Uranus mission. So it's in there. I suspect it will not happen in the decadal timeframe, at least as a flagship. However, there is interest in proposing a New Frontiers class mission that is $1 or $1.5 billion class mission that might even be able to go and look for life at Enceladus. We'll see.
Any other questions?
What do you think would be the most exciting data you could get? What would be the closest thing to really showing strong evidence of habitability, if not life?
Yeah, well, I tried to emphasize that it's not just one measurement. So that's my first attempt to weasel out of answering that question. I'm personally excited about the prospect of seeing seamounts or not in the gravity data. That is, we'll get love numbers to some high order, and I hope that those will show whether or not there has been volcanic activity in the interior. It's a little bit of a weird situation because if you determine that there are not seamounts of a certain size, you've actually made a good argument that the interior is warm enough that such mountains would relax. So have you then argued that there's volcanism or not? So in that example, you would then also want compelling evidence that things have been, materials are in the ocean that could only have been put there by high temperature water rock interactions. So in that sense, in some ways, the mass spectrometer data are most exciting to me in the astrobiology sense. This is being recorded, and I don't want to say too much about one particular instrument in case someone gets mad at me. But I do like the mass spectrometer. But the other thing that's really exciting from the geophysical sense is being able to see solid state convection in the sort of 3D tomographic view we're going to get of Europa's ice with the radar. We're going to have all these different swaths that we're going to see through, and each of them will be a cross section through the ice. It'll be a little bit complicated because there's a lot of different reflection horizons that'll come up, but those are some of the things that I'm excited about.
There's another question online. Would the Clipper be able to study tests of the equivalence principle by looking at the roots of Jupiter?
Okay, so this is me talking to a high energy physics audience. I think this is getting at relativity. Maybe someone can elaborate on that question for me. I will say that we have time delay to deal with. We have to account for gravity effects in the way the mission is designed, but I don't think that's what's That's what's being gotten at here. Anyone else want to elaborate on this question, or does the questioner want to elaborate? I like that you have the same initials that I do.
Yes, Sri, do you want to elaborate?
Yeah, hello.
Hello.
Yeah, I was thinking that the moons of Jupiter might offer a good test of the equivalence principle if you have such an integrated system. It was just a question I was wondering whether you were thinking about such things.
I think the answer is no. There is interest in the long run of putting corner cube reflectors on the surfaces of these moons and understanding the tidal exchanges between them, but I'm not sure if that's what you're getting at.
Okay, thank you very much.
Yeah, I guess like are there still uncertainties in the gravitational interactions of the system, either because of lack of measurements or because like the models?
So there are absolutely uncertainties with the gravitational interactions. I think at the fidelity of the speaker's question, the answer is we won't be able to see those things. So the sensing of the interior depends partly on the timing, like having really good knowledge of time as the spacecraft flies by, and that requires having an ultra-stable oscillator that Europa Clipper will not have. JUICE will do a lot better job at looking at geophysical questions that might be related to the speaker's question, not least because it's doing an interferometric experiment with multiple observatories on Earth to try to figure out the interior structure of Ganymede to some high precision. So that'll give us a sense of both the static and dynamic gravity field of Ganymede. That'll be interesting.
Yeah, well, maybe we can continue further discussion upstairs in the lounge.
That sounds good.
Yeah, let's thanks.